Today we are going to look at the first three problems of today's biweekly contest. The first problem is alternating groups. It states that we are given a array of zeros and ones called colors, where zero means red and one means blue, and we are to find three continuous tiles, number of three continuous tiles which are alternating in colors, right? So, for example, here we are given all ones. So there's nothing alternating. And this is a circle, so the last one is next to the first one, right? Similarly, if we are given second example, here if we see 0, 1, 0 is one alternating time, size of 3. And similarly, if we move forward, uh, this is not alternating, this is not alternating, and lastly, this is alternating 1, 0, 1. This is alternating, hence we increase the count. So there are three alternating groups here. Right? It's a straightforward problem. We can do it in linear time. Let's see how we can do it. First, we initialize answer equal to 0. We go through we enumerate the array because we are going to use I, right? So if uh, we can have three variables, I plus 1 can be out of bounds, but since this is circular array, we can just mod it with n. And let me declare it here. And let me also write it here instead of index of size. And the third variable will be colors of I plus 2. Again, this will be out of bound. This can be out of bound. That's why we mod it. Now we check if first is equal to third and first is not equal to second. Okay, so this means it's alternating. We can do this since we are given only three continuous tiles as a requirement. But if we are given k, which we are in the third problem, then we'll do it differently. Answer will increase. We return it. This is linear time and constant space. Uh, let's see if it works. Does the second problem states that we are given enemy energies and current energy, right? And we can do two operations over it. The first operation is we can choose any of the enemy energy, which we have not chosen previously, and we can uh, check if we have, if we have the current energy greater than the energy that we are choosing. If it is, then we can just decrease the current energy by that energy amount. So basically, what we are doing is choose for element or enemy energy, and we can do two things based on what the current energy is at. If it's greater than enemy energy or if it's smaller, actually greater is fine for the first case. Enemy energy, in that case we basically decrease the current energy by the enemy energy amount that we have chosen. But if it's greater than equal to, and if it's smaller than the enemy energy, in that case we can do two things. So here there are two divisions. The first division is we can see if our points, so there's something called points. If our points is 0, then we can just choose any energy from the enemy energy again, which we have not chosen earlier, and we can basically, oh, actually, I missed one part. Here, if we are decreasing the current energy by the enemy energy, so if we have satisfied this condition, then we increase a point, right? So we increase this point. Now, if the the first condition is not satisfied, then we see that if the points is greater than equal to 1, at least 1, in that case, we basically increase the amount of current energy by the amount of enemy energy that we have chosen, right? And we mark this. So mark this enemy because we have chosen it. Now we can't choose it again. Or we can, yeah, that's it. These are the two conditions. If we are meeting it, then it's fine. If we are not, then uh, we break and we return the answer, whatever points we have. Now we have to solve this optimally so that we have maximum points as answer, right? So maximum points, when we'll get the maximum points. If we look at it, if we look at an example that will be pretty easy to come up. So this is a good example. Here we can choose any enemy, right? But what do we choose? We choose the enemy which is, more likely to fall into this condition, right? Satisfy this condition. So we need the enemy energy which is smaller so that we can increase the points. And here the second condition, if we see, then we are just taking the energy of the enemy energy, right? And we are marking it. So eventually we want the maximum enemy energy here. So we see that if we sort our enemy energy array, we solve basically we solve our problem of which enemy to choose at what time. Right? Since we are not marking, if we are choosing a enemy energy which is smaller, basically this one, such that it falls into this condition, then we are not marking it. We can choose it again and again until we exhaust the current energy, right? Basically, we can have two pointers. Uh, the first pointer is the first condition, the second pointer is for the second condition. And we have something called points, which is initially 0. Our current energy is initially given in the question, that is 2. Now we see that current energy is equal to the energy which is smaller. Then we increase the point, we reduce the current energy. Now current energy is smaller. Then we get the energy because we have at least points, at least 1 point. If we don't have at least 1 point, then we can't do anything. We just return whatever points we have, right? So now we are said that we are marking the enemy. So if we reduce j, then it's basically we are not going to increment j at any point of time. So we are basically ignoring this, hence that's equivalent to marking the enemy. And we have increased the current energy to 3 because we have chosen this enemy energy. And now we again can choose this, and then we get 1. We increase the point. Now the current energy is again smaller than the first enemy energy. Then we again choose this. We we increase the current energy by 2, and At last, we increase one more point, exhaust our current energy, and we return, sorry, we increase the point and we return 3. That's it. Right, so let's get into the code. So let's start coding. Sort this, okay. Alright, so let's code it. We sort the enemy energy. Uh, Again, this will solve most of our problems. Uh, we'll have a point initialized to 0. We have first, uh, we don't even need I. We can just use 0 at the places because we are not going to increment I at any point. And we are going to have j, which is n minus 1, and n is equal to size, and we are going to run a while loop till the point I is less than is greater than equal to, sorry, I is less than equal to j. I say equal to because, for example, in this one itself, we end up having I equal to j, and then still, I mean, take into account of the energy. That's why I is less than equal to j, and we check if the current energy, basically the second condition is what I'm trying to check here. Enemy energy is, if it's greater than, and sorry, if it's smaller, enemy energy is greater than the current energy. In that case, we check if points equal to 0. In that case, we turn 0. Otherwise, we just increment current energy by this amount. Yeah, by this amount, we reduce T. Else, we check if the current energy is greater than equal to the enemy energy. In that case, we don't even need that because else condition is that it's a great. It's less, if it's not less, then it's going to be greater than equal to. In that case, we increase the point, we reduce the current energy by what amount? By the amount we have chosen. And yes, that's it. We return the points. Let's see if this works. It does. Now there's one more optimization we can do. Let's see what it is. This will give TLE. Oh, sorry, this is long, right? So points will be long, and I guess that's it. So why this will give TLE is because we can do one more optimization. Since we have to do this, right? Here, there's many times it's going to enter this until current energy is exhausted to 0, right? So we can straight away in one go exhaust it to 0. For example, if the current energy is at 6, all right, and I'm at suppose here, just an example, I'm at here, points is suppose 0. So I will run this first condition, which is this one, 3 times until I exhaust current, right? Well, because 6 by 2 is 3. So we can just, instead of reducing it one by one, we can just make current energy increase points by what? By current energy divided by enemy energy. And we basically change current energy to what? We are exhausting it until we have 0 or we have some remainder left there. That is this one. We mod it. Now this will pass. I think this is one optimization we needed. And yeah, it does. So the third problem is basically the first problem, but generalized for K groups. I mean K tiles. So we need to count the number of groups, which number of K alternating groups basically, number of K tiles which are alternating. Right. So this is straightforward. This is I think the same example. Although, so basically, what if we solve this mentally? We are trying to form a window, right? We are just trying to form a window, and then we are seeing if that window is alternating or not. So we can do that. We can do that using 2 pointers, or there's a better data structure as well, which is a deck. Basically, if we have a deck and we add elements to it one by one until the point where the size is reached to k, or if we break the alternating case, right? If it's not alternating, then we remove all the elements from the deck and we initialize it to back to 0, right? And at the point where we have the size equal to 3 and it's alternating, that's why it reached to that size, so we increase the answer by 1. Similarly, we'll do it again and again. Till what point? That's the question. So if we take an example, let me take a new example, 0, 1, 1, 0, 1. Suppose this is the example, all right? Then how many number of windows that we can form? Mind that this is a circular array, and the first and the last position that it lies right back to back, right? So basically, we are if the window size is 3, we take the first thing. This is one window. This is another. This is another. But now that we've reached the end of the array, shall we stop here? No, because we can still form this window. Or actually, the last window is this one. This window is still a new window that we can form. This is basically 0. The first element is here. We can form this window as well, right? I think this is one window. This is second window, third window. This is the fourth window which we can form. This is the fifth window that we can form. Now, if we form another one, then we basically are forming the first window again. So how many windows have we formed? The size of the array was 0, 1, 2, 3, 4, 5. The size of the array was 5. K was 3. The number of windows we have formed is 1, 2, 3, 4, 5. 2, 3, 4, 5. The number of windows we have formed 5. But how many elements we have added? Because we are going to use Q, right? We don't have 2 pointers. We just add all the elements that are part of the window. And we keep copying if we exceed that size. So how many elements have we added? 1, 2, 3, 4, 5, 6, 7. So we are forming, I mean, adding more elements than n. So our loop will run like this. Initially we have deck, we have the answer, we initialize the pointer, we have a n variable, and this will run from n plus k minus 1. Why minus 1? Because this is the color sort size, that's why we are subtracting 1. This should be this should be equal this many elements we are or we can just move this and yeah, this is also the same thing. This many elements you have to add and we first check if the deck is equal to the size of k. If it is, then we increase the size. If it is not empty and if the deck, the back of the deck is equal to the current element that we have at hand, then it means it's not alternating, right? Also, this I can be out of bounds, so we can declare an index variable and we can mod I with n. Now, colors of index, it's equal, then we clear the deck. Also, here, if it's equal to the size k, then we pop the uh, first element, the front, and we push it here, push back, colors of index. And we return the answer. Let's see if this works. The time complexity will be O of n, and the space will be O of n again. I think two pointer will be O of 1, the space complexity wise. This works, and thank you guys.